So now in this lecture we will define precisely an example to cover the buttermilk case. So let's say precisely the model to cover the buttermilk case. So this is called the one-way random effect model. So here the premise is we take n identical observations from R subjects. Okay, so we take n identical measurements from R subjects. Let's say R. Very good. So what's the model going to be like? The model is going to be Yij is going to be mu plus alpha I plus epsilon ij. Allow 1 less than equal to I is less than equal to my R right here. There's R groups. And then allow n samples. So 1 less than equal to j less than equal to n. And I'll assume again like before, this until now we've done this, epsilon ij's were all distributed as normal with mean 0 and variance sigma squared, and they were independent. This is the standard model. But in this, to introduce random effects, I'll think of alpha i's as also normal. So what we'll do is we'll think of alpha I as distributed as normal with mean 0 and variance sigma squared mean. This again for 1 less than equal to R. So let's say 1 less than equal to I less than equal to R, 1 less than equal to j less than equal to n. And we might be interested in the population mean mu. Like, is it 0 or not 0? Right. So what are the questions of interest? The questions of interest is that is mu 0 or not? Right? Can we test it? Right. Alternatively, another question we're interested in is that since alpha is random, is the variance 0? Is sigma squared mu 0? Is there a random effect to the model or not? So how do you define a test to understand these two concepts? That's what we'll do next. Before that, let's discuss some implications of this model. Suppose you place a model like this where the alpha is also random. So here are implications. So here are some implications. So one thing is there, so because of the way I've set up the model, let's go up a little bit up so you can see the model. The way I've set it up, the first thing you observe is that our Yij's are no longer independent. Okay, no longer independent. Because of the dependency in alpha. Even if the epsilons are independent, why? This is because of the following fact, right? You look at the covariance of Yij and let's say YKL, right? This is going to be equal to what? This is going to be equal to sigma squared mu delta IK and sigma squared delta LL IJL. Right? That is, if J is equal to L, it will be sigma squared. If I is equal to K, you'll have sigma squared mu, and otherwise it will not. So delta Ij is equal to 1 if I is equal to J, and 0 otherwise. That's the definition of right. So that means the random variables Yij, or the model doesn't make the Yij's independent. That was the case in the fixed model. Right? So this makes, so what will this happen? If moment you have something like this, several things happen. It makes the maximum likelihood estimate method more complicated. It's not so simple. So you can't just do a sort of a least squares. Not only there are parameters in the mean, but in the covariance as well. That's what we observed here. Right? So so note that earlier before in the ordinary least squares, that ordinary least square method, we had only parameter to estimate was sigma squared. That's easy, right? Because the variance covariance matrix was sigma squared I, because all the random variables I were sigma epsilon ij were assumed to be independent. Right? So that's one contrasting feature and implications of this model. The moment you make alpha is a random, you will have this problem. So, very good. So, but the analysis is similar. It's not very different from the original analysis. So let's just do a one-way ANOVA table for this. Let's say one-way random ANOVA table for this. It's similar to the, there's no difference from the fixed effect, but I'll do the table properly for you to show it. So the source will be, let's do a source. The source will be treatment and errors. Let's do treatment and error. That's the source. Source of the table. First column is that. The second column will be it's the sum of squares. Let's write sum of squares. Let's write sum of squares. Right. So what are sum of squares? One is sum of squares treatment. I'll just call it as sum of squares treatment. So what's that going to be? That's going to be again the sum from I equal to 1 to r, right? N times I'll do yi bar, right? So fix the I and take the mean over thing, and then minus the overall mean, y doubled. Right. So I'll give it the name sum of squares. Right? So again here I'll have a degrees of freedom. So this we already seen before. Just like in the other case, I'll have this is r minus 1 degrees of freedom. Right. That'll be one right? And then I won't write the fourth column because I have no space here, but I'll write below. Then the sum of squares errors will be what? The error sum of squares will be just again the same, the whole thing, right? So I'll have sum from I equal to 1 to r, sum from j equal to 1 to n. I'll have the yij minus y dot bar, yi dot bar square. And here the degree of freedom is n minus 1 times r. And this is something one can show. It's not hard. Let's say, so some exercise I'll write down. So let me write this down. Exercise right here. Let me put another column right here. So that's exercise at the top. And you can check that its mean sum of square, that is its expected value, that is expected value is going to be what now? It's going to be, in the first one, you'll have, if you take the mean across the E of SS treatment, you can check it's going to be sigma squared plus n times sigma squared mu. That's just the mean. The second one, you'll just get sigma squared. That's the mean. So this ANOVA table is still very useful for the particular model that we have in mind. So you can use the same F test, right? So the only change here is that the expectation of sum of squares treatment reflects the randomness of alpha i's. So you can do the same effect, same F test. So let's say H naught is the one when sigma squared mu is 0. That's what you want to test. Let's say there's no variance, so the sigma squared. So it's easy to see that the mean sum of squares treatment means, let's say I think I'll call it mean STR. Sorry about that. Mean STR treatment divided by the mean squared error. So you divide by appropriate. It's just the same as SS treatment by r minus 1, the whole thing divided by ms error, mean squared error, sorry, SS error, sorry, SS error by n minus 1 times r. This is distributed under the null hypothesis, is distributed f of r minus 1 n minus 1 times r. So you can use this to test whether the sigma squared is 0 or not. So after it's large enough, you sort of discard it. There's one more thing you can do now. Once you this particular model, so let me just go back up. So there's one more thing you can do. So now here in this model we have mu plus alpha I plus epsilon j. So this particular test that I did gave you an inference of how to handle sigma squared. Right? Now I can do the same thing. I can understand how to inference on mu. Like, can I test for mu from this model? Right. So that's what I wanted. So now here, let's just do a simple inference on mu. So what's the first thing we know? We know the overall mean should be mu, right? So it means we know that if I take y bar dot dot, that is summation from j equal to 1 to n, I equal to 1 to r, you divide by the total number, that's y double dot bar. The mean of this has to be the same as mu, the way I define the model, right? Because both the mean of alphas and sigmas are all at epsilons are all 0, so this mean is just on mu. That's one thing we discovered, right? And we also can check that the variance of y or dot dot is going to be equal to n times sigma squared mu plus sigma squared divided by n. So simple exercise to try. I think it's Rn. Sorry, I made a mistake here. It's R times n. Very cool. Right? So therefore, once you have this, and because of the normality assumptions on the model, we know that this will imply if I take y bar dot dot minus mu, and I divide by square root of these. Since I don't know the variance, I'll do sum of squared treatment, because that's the mean of this SS treatment plus that. So I'll estimate it by SS treatment because I know the variance, divide by r minus 1 times r times n. That will follow. So that will follow. Let me just move it up. That will follow the t distribution, that is t times r minus 1 degrees of freedom distribution. Right? So why do we get r minus 1? That's because we record many observations for each interval. So you know that the yi bar dot goes to mu I in that sense, and which is mu plus alpha I. So to anything learn about mu, we only have r observations. That's why you get r minus 1, guys. So, and you can do you can sample more and get but you can't narrow the constant interval for mu. That's all you get when you take more observations. So the r is kind of determines how large or small the constant interval can be. It's kind of fixed. The last thing, let's say we want to estimate sigma squared mu. Let's just do that in a second. Let's go next. Let's go new page after. Oh, sorry, page before. I made a mistake here. Let's see. Okay, there's no problem. So here, if I want to estimate sigma squared mu in this model, so how would I do that? So from the table, from the ANOVA table, you know that sigma squared mu, sorry, let me just is the, if you do the algebra from there, you know sigma squared mu is equal to the expected value of sum of squares treatment, right, divided by r minus 1, and then you subtract the sum of squares error, divide by n minus 1 times r, and the whole thing you divide by 1 over n. So that's the estimate for, that's sigma squared mu from the calculation there, right? So a natural estimate for sigma squared hat would be exactly that, right? Would be just take exactly the above, right? So let's just take that, let's copy that down. So let me just copy this down, would be exactly, let me copy it. How would I copy it now? Let's go edit, let's go copy, go here, edit, and let's say paste it with this, and you divide this by the whole thing by 1 over n. So that's an estimate for the sigma squared. Right? And but there's one danger here, right? The one danger is that the estimate could be negative, right? So some estimate negative. So the caution is that sigma squared hat. So let me erase it properly. Let me write it properly. That sigma squared hat mu could be negative. That's something you must keep in mind. There's a possibility. So there are difficulties of random effect models. Should be careful about this. This we can't do.